Hi, this is Jeff Spence, your Math 120 instructor for the Community College of Denver, and this is our video lecture over Section 8A, which in Chapter 8 we start to look at exponential growth and decay. So in 8A we want to compare the linear growth and decay versus exponential growth and decay. And remember in Chapter 9A and 9B we were looking at linear functions and linear growth and decay. So linear growth occurs when a quantity grows by the same absolute amount in each unit of time. So like the price of a car goes up $500 every year. So that's an absolute amount. Okay, $500 every year. So that would be linear. Exponential growth occurs when a quantity grows by the same relative amount, that is, by a same percentage in each unit of time. And exponential growth, the way we're going to see this, is very similar to when we were doing our financial formulas with compounding, and the rate of interest was our growth rate, our percentage. So we're going to, whenever we have exponential growth, we're going to be looking at growing by some percentage at each unit of time, per year, per month, per second, whatever. So there's a difference between an absolute, which is an amount in each unit, versus a percentage in each unit of time. So straight town population, here's an example of just a picture of what it looks like. Straight town grows by the same absolute amount each year, and Power Town grows by the same relative amount each year. So you can see a linear pattern for straight towns, a straight line. Looks like it's growing about 10,000, about 12,000 in the first, say, 27 and a half years. Okay, and it continues to grow at that same rate, up this many over this many. So, but Power Town grows by the same relative amount. So this is very much like compounding interest. When we get to our first doubling, now we're doing a growth percent of a larger amount. Okay, so it continues to grow at a faster rate, and then the population really becomes exponential. In each of the following situations, so what we got to do for the rest of this section 8A is just determine if we recognize linear or exponential growth. So, or decay, excuse me. So state whether the growth or decay is linear or exponential and answer the associated questions. So the number of students at Wilson High School has increased by 50 in each of the past 4 years. If the student population was 754 years ago, what is it today? And then they have A, B, C, D. We're going to go to the answer for A. So if the number of students at Wilson High School has increased by 50 in each of the past 4 years, if the student population was 754 years ago, what is it today? Well, that is definitely linear growth, and because it's an absolute amount, 50. And since it's grown 50 students for 4 years, we just take 4 times 50, that's the growth, 200 students, and then we add that to the 750 that we started with. This is very much a linear problem, so the population at that school is now 950. Okay, next one, B. The price of milk has been rising 3% per year. If the price of a gallon of milk was $4 a year ago, what is it now? So that is definitely exponential growth because we're rising by a percent. So if the price was $4 a year ago, it increased by 3%, so 0.03 times 4, 12 cents is the increase, making the price $4.12. If we wanted to look at the growth for next year, we would take 0.03 times $4.12, and that would be a little bit larger than 12 cents, and we'd add that on. So exponential growth continues to grow at an increasing rate. All right, part C. Tax law allows you to depreciate the value of your equipment by $200 per year. If you purchased the equipment 3 years ago for $1,000, what is its depreciated value today? Well, this is definitely a linear decay because depreciation means the value goes down. And we want to see how much it went down over 3 years. So we take 3 times 200. That's 600 depreciation. So the value decreases. Take 600 from 1,000 and it decreases from 1,000 to $400, a linear decay. Depreciation is a pretty common term. It always just means that something is going down in value, so it's a decay. The memory capacity of state-of-the-art computer storage devices is doubling approximately every 2 years. If a company's top-of-the-line drive holds 16 terabytes today, What will it hold in 6 years? This is a great question. So since it's doubling, that's the same as 100% increase. So the 2-year doubling time represents exponential growth. If we're going to double every time, if we're going to double every 2 years, then we're growing 100% from what we were 2 years ago. So it's definitely a exponential growth. So with a doubling time every 2 years, the capacity will double 3 times in 6 years. Hopefully that makes sense. From 16 terabytes to 32 terabytes is the first doubling. From 32 terabytes to 64 terabytes is the second doubling. And from 64 terabytes to 100 terabytes, 128 terabytes after the third doubling, 6 years. So it would be 128 terabytes. Then the last one, the price of high definition TV sets has been falling by about 25% per year. That's definitely not true, but if it was, that would be an exponential decay. If the price is 1,000 today, what can you expect it to be in 2 years? So since it's decreasing by the same percentage, that's exponential decay. So for the first year, it would go from 1,000, the price will fall by 25%. So 25% of 1,000 is 250. Therefore, the next year's price will be 750. Take 250 from 1,000. Then the following year, the price again will fall by 25%, but it's 25% of 750, not 1,000. So 25% of 750 is 187.50. So the price after 2 years will be 750 minus 187.50, 562.50. So those are the examples that you're going to have to decide between if we have linear or exponential growth. Maybe answer a couple basic questions within the first year or two or month or two. In 8B, we'll start getting into the formulas, how we actually find the price or the cost or the value or the population after many years. Good luck, and we'll see you soon.